continue with our lesson on stoichiometry today. The other day you were introduced to stoichiometry and we started just some very simple conversions. For example, converting from moles of one substance to moles of another, moles of one substance to mass of another, mass of one substance to moles of another substance. And where this is all leading in regard to our stoichiometric calculations is that we want to be able to convert from mass of one substance to mass of a different substance, because that's what you would be doing in the lab. You would be provided with the masses of two or more substances. You would react those substances together and you would generate one or more products. So we want to learn how to do this first on paper, and then you'll be able to do it in the lab. Later in the week, we'll get into limiting reagents as well as theoretical and percent yields, and we'll be doing this type of analysis in the lab next week, and it is a very good lab that I think you will enjoy. In regard to your lesson, one thing I do want to reiterate is very often if you look at any textbook on stoichiometry, they will immediately jump in to mass conversions, and the kids really struggled with it initially when you try and just springboard right in, and that's why I did much simpler conversions with you yesterday, where we did mole to mass, and mass to mole. In a mass conversion, it's going to be similar to the mass to mole conversions that we talked about, with one additional step. So in a mass conversion, you'll be converting from mass of one substance to the mass of another substance. The steps to carry out this type of conversion are listed here. Again, just like in the do now, you always write a balanced chemical equation to begin. Figure out what you're given and what you want to know, and then set up your framework. Let your units drive your problem. You're going to be given mass. You're first going to convert to moles. Mole ratio allowing you to go from one substance to another, then mole to mass as the last step. So we're basically putting everything we talked about together in this mass to mass conversion. The framework, for those of you who need a reference point, is shown here. You're going to convert mass to moles of the same substance. That's like what we did back in Chapter 7. The mole ratio that we learned about yesterday, that is the time where you go from one substance, let's say Q, to a different substance, let's say R. That's the only time you can have numbers other than 1 in those fractions, because those numbers are coming from the coefficients. Mole of one substance to the mass of the same substance, just like in Chapter 7. I'm going to walk through this, and then we're going to do several problems very slowly so you can see exactly how you go from point A to point B. It says, what mass of oxygen gas? Is that my given or my unknown? Definitely what you're looking for, the unknown, is required to react completely with 14.6 grams of solid sodium. That is my given. Here's my balanced equation. Classify that. It is synthesis, a specific type known as oxidation. You got it. And again, mastering those previous concepts that we've talked about is critical to move forward. Here's your given. Here's your unknown. A mass-to-mass conversion is a three-step problem. You're given the mass of sodium. First thing you're going to do a mass-to-mole conversion of the sodium. Where did the 22.990 grams come from? Periodic table. Once you get to moles of sodium, here's where you're going to do the mole ratio, allowing you to go from moles of sodium to moles of oxygen. Where did this 4 come from? Coefficient in the balanced chemical equation. This is a mole ratio. Now you're at moles of oxygen, mole to mass conversion. Now oxygen on the periodic table has a molar mass of 15.999 grams per mole. So where did 31.998 come from? Multiplied by 2, because oxygen is a diatomic element. All right, there's your setup. Little tricky to follow, so let's slow it down and really walk you through. On the first problem, it says, and I'll read it as I write, and I'm going to go sideways here because when you have these three steppers, they are very long. We've got sodium metal reacting with chlorine gas to generate sodium chloride. This is a basic concept that we've already talked about, and you should not have any issues writing the balanced equation of a synthesis reaction. It says if 20.4 grams of sodium metal is mixed with an excess of chlorine gas, what mass of sodium chloride should be generated or produced? What's the given?
20.4 grams of sodium metal.
So that's my starting point. I always start with my given. What do I want to know?
Mass of sodium chloride.
I want to know the mass of sodium chloride. A mass-to-mass problem is 3 steps. You don't have to memorize steps. You just want to make sure that your units drive your reaction or drive your calculation. I've got grams of sodium here. Look up at the screen. I've got grams of sodium here. I need grams of sodium here. Wherever I have grams of something, in almost every instance except with density, I will have 1 mole of it in the other part of the fraction. And this piece from the periodic table, 22.990 grams. This is a mass to mole conversion for the same substance, in this case sodium. Note the cancellation of unit and substance. To go from one substance to another, I always use what? Mole ratio from the balanced equation. I've got moles of sodium here. I'm going to have 2 moles of sodium here to 2 moles of sodium chloride here. Again, the mole ratio is the only time you have 2 different substances in the same fraction, and the only time you may have numbers other than 1, because these come from the coefficients in the balanced equation. Now I'm at sodium chloride. I want to get to mass. I'm at moles. I want to get to mass. This is a mole to mass conversion of the same substance. 1 mole of anything is equal to its mass in grams I would simplify this down. It just makes life a little bit easier. And you get 51.9 grams of sodium chloride. And again, this is a mole to mass of the same substance. Taken all together, you have the conversion from mass of one substance to mass of another substance. What you will also learn later in the chapter is this is a theoretical yield. This is the amount of substance, and it's got to be a product if it's a yield, that you should be able to generate in a perfect world. We'll compare our theoretical yield to what we actually generate in the lab to calculate a percent yield and get an indication of how efficient of a job we did in the lab. In college, you are graded on your percent yield. Let's take another one so that you can see it again. Number 2 says barium chloride reacts with lithium phosphate. What type of reaction is this? Double replacement, and most of you got A's on the previous test or very high B's. So you do appear to have mastery of this concept. There's your balanced equation. It says if 32 grams of barium chloride react with an excess of lithium phosphate, what mass of the barium containing compound should be generated? What's your given? And now let's be careful. What do you want to know? You want to know the mass of barium containing compound that gets generated. If it gets generated, you're looking at a product. This one contains barium. So make sure you go for the right substance. Question on the setup. What's the first thing we need to do? Convert to moles. 1 mole of anything is equal to its mass in grams from the periodic table. Now you're at moles. What will you do in the next step? Mole ratio from the balanced equation. 3 moles of barium chloride to 1 mole of barium phosphate. So there's the mole ratio. And now you have a mole to mass of the same substance back from chapter 7. 1 mole of anything is equal to the mass in grams. I'm going to write this a little higher just so it fits. Be very careful with your calculator now. You don't want a calculation error. If you have more than one quantity in the denominator, make sure you parenthesis it off. And that's 30.8 grams. questions here? Anything with the setup? Again, let your units drive your problem. You'll see the cross cancellation, and now you understand why I was so insistent that every substance be labeled, because now you're seeing places where you have two different substances, and it's really the only way to keep track. Why don't you try C, see if you can do it. I think you will. Only look up if you have your answer, bottom of the screen.
That's exactly right. Exactly. I haven't taken this since round 4. I had you take this on this.
See if you put everything in its right place. It was the same equation that we had already balanced, mass to mass conversion. That's most commonly what you will see asked. On your quiz, I'll ask a little bit of everything to make sure you can do every variety, and it probably makes it a little easier for you. But this is typically the type of thing you would be asked. You would be given the mass of one reactant and asked for the mass of a product. Later on in the chapter, you'll be given the mass of two reactants, and you'll have to determine which one to use, and we'll get into that. Questions here? This is as far as your quiz goes. I'm going to show you one additional type of stoichiometric calculation today. It's not on your first quiz, but it is on your second quiz. It's very, very simple. We are just going to build upon this concept here and integrate density into it so that we can either find the volume of a substance or convert the volume of a substance to the mass of a different substance. For example, in the equation shown here, we have determined the mass of lithium chloride. If I wanted to know the volume of lithium chloride, I could do that by integrating the density piece into it, because we know, for example, that density is equal to what? Mass over volume. So we can do conversions where we're either given volume and asked for the moles or mass of a different substance, or we can convert, for example, from mass or moles of one substance to the volume of a different substance. And typically what you're going to see is when you're dealing with volume, you'll very often have a gas. Keep in mind that density is mass over volume, and we're going to link volume into our stoichiometry type conversions through density. Sometimes you'll use density directly, other times you will use the reciprocal of density. If you let your units drive your problem, you'll be very successful here. We're going to walk through 3 examples, and then you'll have a lot of practice time. It says in space shuttles, the carbon dioxide that the crew exhales is removed from the air by a reaction within canisters of lithium hydroxide. On average, each astronaut exhales approximately 20 moles of carbon dioxide daily. We want to know what volume of water should be produced from 20 moles of carbon dioxide if an excess of lithium hydroxide is present. The density of water is 1 gram per mil. The equation is provided. We will go ahead and balance it. We've got carbon dioxide plus lithium hydroxide that you find in these canisters. Reacts to generate lithium carbonate and water. And we're balanced. We want to know the volume of water that should be generated. When you're trying to determine the unit, if they don't specify how they want the unit, look at the density. The density is 1 gram per mil. And because they didn't specify how they wanted the volume, I'm going to use mils because it's going to be easier. What is your given? 20 moles of carbon dioxide. Remember, your given will have a number, a unit, and a substance. We want to go from carbon dioxide to water. if you're ever given moles, what is always the first step in a stoichiometric conversion? Mole ratio from the balanced equation. 1 mole of CO2 to 1 mole of water. And we ultimately want to know the volume of water, and we picked mils because it was the denominator unit in my density. In order to get to volume, we're going to have to go through density, and the unit for density is grams per mil. I'm at the other substance, but I'm in moles. So next I'm going to go from moles to grams. 1 mole of anything is equal to its mass in grams on the periodic table. I don't care if you use 18.0148 or 18.015, whatever rocks your world is fine. You'll get similar results, doesn't matter. So thus far, we've basically done a mole to mass conversion like we talked about the other day. Here's the new piece. This is going to be my density factor, allowing me to convert from mass to volume of the same substance. The density is equal to 1 gram per mil, and this is for water. So I'm going to expand upon the way density was written so you can see how to place it appropriately in the fraction. So density is 1 gram, keep that numerical value with gram, water, for every 1 mil of water. I've just expanded upon the density to make it look like a fraction similar to what we have here. And I need to decide how to place that fraction appropriately in this last step. I've got grams of water here telling me that I need grams of water here. The number that was provided initially is what always stays with the grams. And I'm going to put 1 mil of water on top. So this density factor, when you're solving for volume, is the reciprocal of the density, allowing the grams to cancel. And you have 360 mils of water. So when you're solving for volume, your last step will be the reciprocal of the density. The next problem is grossly similar. So it's really critical to label everything in these types of calculations. So in terms of the next problem, same balanced equation. They're giving us 325 grams of lithium hydroxide reacting with an excess of carbon dioxide, and we want to know the volume of water that should be generated. And for the same reasons we listed previously, we're going to go to mils of water, and again, that's because the density is given in grams per mil. What should I do first? Get to moles. 1 mole of lithium hydroxide. Once you have moles, how do you go from one substance to another? Mole ratio, we've got 2 moles of lithium hydroxide to 1 mole of water. Once you're at moles of water, you need to get to the mass of water just as we did previously. And what's the last step to go from mass of water to volume? We're going to do the reciprocal of density right here. We expanded upon it previously. If you have more than one quantity in the denominator, be sure to parenthesis it off so you don't make a simple calculation error. So when you're solving for volume, it's exactly as you did previously. In the last step, you multiply by the reciprocal of density. So what would happen if we flipped the problem around and you were given volume and asked for mass? Where would the density factor go? In the front. So it would be your first step. So last problem we want to look at here. It says the reaction that causes cake batter to rise involves the production of carbon dioxide from sodium bicarbonate when it reacts with acetic acid. We want to know what mass of sodium bicarbonate is consumed when 7.14 liters of CO2 is generated. The density of CO2 is 1.10 grams per liter. What's my given? The equation's already balanced. My given is 7.14 liters of CO2. And what do I want to get to? You can do it with liters because they gave you the density of CO2. The density of CO2 is 1.10 grams per liter, making it very easy to do. The equation's already balanced. Here's the only difference. If they give me volume, my density factor is up front. Now, if liters are given, what goes in the denominator of the fraction? Liters. So that's just going to be 1 liter of CO2 and 1.10 grams of CO2. Try and continue.
Please listen very carefully to the following announcements as Mr. Benham will.
Try and continue with the rest of the problem.
All boys varsity soccer players need to report to the main office immediately when the bell rings for lunch for a mandatory meeting. And that is from Coach Regula. The Science National Honor Society will meet right after school today, January 24th, in room 7212. Please see Mr. Semmelmeyer for more details. Teachers, at this time, if you have not done so already, please pass out all report cards to your 5th hour students. Also at this time, please turn on your TVs to prepare for a video that will be shown to show students and teachers how GPA is calculated. Thank you and have an awesome afternoon. here in Cobra Country.
I don't ever have it also not community program.
So as you drive this problem, once you use density up front to convert from volume to mass, this becomes a mass-to-mass problem. See if you can drive it. See if you can drive that problem. I'll reveal the answer. Please don't look until you've got it. And at the end of this lesson, you should be very comfortable with a mass-to-mass conversion once you've practiced it. The volume piece will be on the second quiz, not the first quiz, but mass-to-mass is fair game.